Have you ever stopped and noticed how some things in life just change with this really steady, predictable rhythm? Well, it turns out there's a whole mathematical language that describes exactly that. And once you learn to speak it, trust me, you'll start seeing these patterns absolutely everywhere.
So let me ask you this. What could a taxi ride and digging a well possibly have in common? It sounds like the setup for a really weird joke, right? But the answer actually unlocks this surprisingly powerful idea in math, one that connects things from your daily commute all the way to your long-term savings.
So just take a look at this taxi fare. It starts off at 15 rupees. After that second kilometer, boom, it's 23. After the third, it's 31. Are you seeing the pattern here? Every single step, each new kilometer, adds exactly 8 rupees to the total. It's this constant, totally predictable increase.
Now, this highlights a really crucial difference in how things can grow. Our taxi fare goes up by a fixed addition each time. That's totally different from something like, say, compound interest, which multiplies by a certain rate. That multiplying creates a whole different kind of growth curve. But for now, we're focusing on that first type, the simple yet powerful rule of constant addition.
So here's our game plan. First, we're going to get really good at spotting this special pattern. Then we'll get our hands on the toolkit to understand it. After that, we'll use those tools to solve some pretty fun puzzles. And finally, we'll see why this pattern matters way beyond any math class. All right, first up, let's give our pattern its official name and figure out exactly what the rules are that make it tick.
This pattern is officially called an arithmetic progression, or AP for short, and it's really just a list of numbers where you get from one number to the next by adding the exact same amount every single time. That fixed number we keep adding, we call that the common difference, and we'll just label it D. It's as simple as that.
Okay, time for a little pop quiz. Look at this sequence, 2, 4, 8, 16, and so on. Are we adding the same number each time? Is this an arithmetic progression? What do you think?
And the answer is, nope, not an AP. See, first we add 2, then we add 4, and then we add 8. The difference isn't common, it isn't constant. This is actually a different kind of pattern, but that's a story for another day.
Okay, round 2. How about this one? We've got -10, -6, -2, and then 2. What's the story here?
Yes, absolutely. To get from -10 to -6, you add 4. From -6 to -2, you add 4. And from -2 to 2, you add 4 again. The common difference is a constant positive 4. This is a perfect textbook example of an arithmetic progression.
Okay, so now we're all expert AP spotters. Let's get the tools we need to actually work with them. And believe me, there are 2 incredibly useful formulas here that are basically superpowers for these sequences.
I mean, just imagine you had an AP, and you needed to know, say, the 100th term. Are you really going to sit there and add the common difference 99 times in a row? No way. There's got to be a better way, right?
And there is. This is the first tool. I like to call it the GPS formula. It lets you pinpoint the exact value of any term, we'll call it the nth term, without having to calculate all the stops in between. All you need is your starting point, A, and that common difference, D. It gives you a direct route to anywhere in the sequence.
Let's take it for a spin. We've got the sequence 10, 7, 4, and we want to know the 30th term. So our first term, A, is 10. The common difference, D, is -3. And we want the 30th term, so N is 30. We just plug those values into our GPS formula, do the math, and bam! The 30th term is -77. No boring counting required.
Now, the other essential tool in our kit is what I call the super calculator. What if instead of finding just one term, you needed to add up, say, the first 50 terms altogether? Well, this formula calculates that total sum, S, for you in one clean shot. It's incredibly powerful.
All right, we've spotted the pattern, we have our toolkit. Now for the really fun part. Let's put these tools to work and solve a genuine puzzle.
Check this one out. We've got an AP that has 50 terms in it. We have no idea what the first term is or what the common difference is. All we know is 2 things. The third term is 12, and the very last term, the 50th one, is 106. The mission is to find the 29th term. So, the secret here is to translate these clues into the language of our GPS formula. For the third term, n is 3, so our formula becomes a plus 2d equals 12. For the 50th term, n is 50, so we get a plus 49d equals 106. And just like that, we've turned our word problem into two equations. It's a classic algebra setup. Now that we have our two equations, we can solve for our two unknowns. First, if we subtract that top equation from the bottom one, the a's just cancel out, which is perfect. We're left with 47d equals 94. A quick division tells us our common difference, d, has to be 2. Now we can plug that value back into our first equation. That gives us a plus 4 equals 12. So our first term, a, must be 8. And now we have everything we need. We just use our GPS formula one last time to find that 29th term. And there it is, 64. That is the power of this toolkit. We started with just two little clues, and from them, we were able to basically reverse engineer the entire sequence to find the one exact term we were looking for. Pretty cool, right?
And this isn't just for abstract puzzles. Look at this real-world case. Subha Rao starts a job with a salary of $5,000. That's our A. He gets a fixed raise of $200 every year. That's our common difference, D. The question is, when will his income hit $7,000? Well, we set up our GPS formula, but this time we solve for n, the number of years. You run the numbers, and the answer is 11. It'll take 11 years to reach his goal.
So, this is obviously more than just a math exercise. Why should we actually care about arithmetic progressions in the real world?
The big idea, the main takeaway, is this: arithmetic progressions are the mathematical language for anything that grows or shrinks at a steady, constant rate. You see it in simple savings plans. You see it in physics, like an object moving with constant acceleration. You even see it in computer science, in the way programs sometimes lay out data in memory. It is the signature of predictable change.
So, the next time you see something changing in these perfectly regular steps, maybe it's the rows of seats in a stadium or a simple countdown timer, you'll know the mathematical pattern that's running the show underneath it all. So the real question is, now that you know what to look for, where else in your world are you going to spot the steady march of an arithmetic progression?